All right, let's get started. Hi, everybody. Welcome to another round of our fellows talks. Um, First up is Camille. Camille, you want to share your screen?
This is our summer 2024 fellowship project, the optimization of the Rucio-SENSE DMM by me, Camille Sicat, with mentorship by Shea Aurora and Diego de Villa. So, start. Current experiments, such as the compact moon solenoid, generate as much as 20 petabytes of data per year. Future planned experiments, such as the High Luminosity Large Hadron Collider, will generate up to 30 times more data. Now, on this large volume of data, it will need at least 100 gigabits per second network speed to be replicated across different physical storage sites, with an estimated 400 gigabits per second needed to transfer between sites in the US. And then this is very computationally difficult with hardware. And assuming that the hardware works, we still need to better optimize our current network usage. Our current model is to just push data transfers through, and if it fails, push again. This doesn't really work, especially since our networks are dominated by large transfers of around 100 terabytes to 100 petabytes, which at a speed of 1 petabyte at 100 gigabits per second will take around 1 day to transfer. This means if transfers fail, the network bandwidth will be taken up by these large data sets. Therefore, we need more accountable network usage if we want to efficiently replicate it across different sites. And that's where software-defined networking comes in. So software-defined networking allows for strong end-to-end accountability, meaning both the site transferring data and the site receiving data are accountable for those services. It also provides the ability to manage different priorities of workflows, which is important for the different experiments done at CERN. If we integrate software-defined networking with our current tools, we can report how much data has been transferred and received between endpoints, compare expected versus actual transfer rates, and identify points of failure in the transfer. This is why we want to integrate it with Rucio and SENSE. So SENSE stands for Software-Defined Network for End-to-End Network Science at the exascale, and allows for customizable multi-domain orchestration for experiments with individual domain science workflows and requirements. It pushes quality of service and routing rules, which are both important for data transfers. And we want to use it in conjunction with Rucio, which is CERN's data management software. It provides scalable data storage, transfer, replication, and other services across different physical locations. And it also provides individualized tagging and tracking for data sets, which is useful. So the Data Movement Manager, DMM, is the interface between SENSE and Rucio. From Rucio, it will grab the source and destination names for transfer from the RSE, the number of bytes, and the priority, which determines how much bandwidth a transfer should get. And transfers are called rules. From SENSE, it will construct peer-to-peer VLANs for each set of endpoints. And while the transfer is going on, it will monitor the status and performance of all data flows. Now then, based on the transfer metadata, such as the mentioned priority, which goes from 1 to 5, DMM will provision network bandwidth for each rule. And it will constantly assess the current bandwidth usage and reallocate bandwidth depending on the priorities of new rules being added or old rules being completed. So if a new rule with the highest priority is added, it will recalculate all of the bandwidth, make sure it gets what it's needed. So our goals for this summer 2024 fellowship is to make DMM more robust. we want to implement DMM's monitoring system to get those metrics that we mentioned earlier with STN. We want to correlate the FTS monitor data with host level information so we can generate performance reports of the metrics described earlier from the combined host and transfer data, obtaining things such as transfer rates, points of failure, etc. In addition, we also want to optimize DMM's interactions with Rucio and its bandwidth allocation algorithm to ensure that our current network usage is more accountable. So to sum it all up, for our current and future experiments with large volumes of data, we want to integrate SDN by optimizing our Rucio-SENSE DMM and making it more robust in order to make sure that our network usage is more accountable and reliable so that experiments can run smoothly with data being transferred and replicated across different sites. Thank you.
Thank you, Camille. Any questions for Camille? All right, thanks again. Up next is Lev. Lev, you want to go ahead and share your screen?
Yeah, sure. Can you see it well?
Yes.
Yep. So this year's proposal is packaging the HEP simulation stack on conda-forge, which will be done by under the mentorship of Matthew Fackert. So to begin with, currently we have 1,2 chain used for energy physics simulation, which consists of Mangraph 5, Fear 8, and Delphis. And sometimes installing these tools can be challenging for new users. And so in order to resolve this issue, so there is a proposed solution, which is use conda-forge packaging infrastructure that allows distribution of complex binaries across multiple platforms through its management ecosystem. And as root and PyFair library with Python bindings have been already successfully packaged and distributed on conda-forge, should be possible to package other components of the simulation stack and distribute them on conda-forge. If this will be done and completed, this will simplify the process of installing these tools and allows it to be installed not only as individual tools, but also as a coherent package environment. And so, as I said before, goal of this project will be packaging as many dependencies for simulation stack on conda-forge as possible. And current project timelines looks like this. For first 2 weeks, I've been refreshing my knowledge and familiarizing myself with conda environment in order to perform task and basically setting up a development environment that will be required, etc. Currently, what I'm doing is adding conda-forge feedstock for Python-free bindings for HEP MC2, which is still widely used despite the fact that HEP MC3 already exists. I'm doing this with in collaboration with Chris Barr, which is the maintainer for this feedstock on conda-forge. And also, as I remember right, it is possible not to package the whole feedstock, but also do just adding a new dependency, Python dependency for this FMC2, but we want to add a new feedstock first because it will be much better. For week 5-6, it is planned to add a feedstock for Python-free bindings, which is also will be done in collaboration with Chris Barr, and then packaging other tools like LHCb and fast jet, but this one is stretch go because, as Matthew said me earlier, we'll need to collaborate with another team, and we will need to reach them first. Start the work on the tool. After all blend tools will be packaged, it is planned to update documentation, provide it with example of using of new already packaged tools. And basically after this will be done summary report for Fellows project, and basically that's it. Planned timeline will be from 3rd June to 22nd August, and that's it. Thank you for listening.
Thank you, Lev. Any questions for Lev? All right, thanks again. Up next is Jordan. Jordan, want to go ahead and share your screen?
Okie dokie. Can you guys hear me okay?
Yep.
Awesome. Okay. Hi, I'm Jordan. I am an undergraduate at the University of Tennessee in Knoxville. I absolutely love particle physics and clean code. So because of that, I am delighted to introduce the Repackaging and Jet Substructure Observable Tools project, which I am working on under the guidance of Dr. Matthew Feichert, super popular mentor, out of the University of Wisconsin-Madison, and Dr. Henry Schreiner of Princeton University. And the tools that are referred, I'm on the right screen, there we go. The tools that are referred to in that big long title are directly referencing two different libraries. Excuse me. Wasserstein and Energy Flow. The first one, Wasserstein, is written in C++, but uses Swig Python bindings. And it's designed to take a lot of really hard, really complicated math and do it all behind the scenes so that experimentalists like me don't have to. So I'm a really, really big fan of it. Specifically, it calculates something called a Wasserstein distance. And that is a distance metric that is used to evaluate probability distributions. It's also sometimes called an energy mover's distance or an earth mover's distance. So that's where the EMD comes from in this image, which was created by the authors of both of these libraries using the second library, Energy Flow. Energy Flow is pure Python. So that simplifies my work a little bit, but it's also huge. In addition to enabling physicists to make gorgeous visualizations like this, it also integrates with some super cool machine learning tools and grants physicists early access to fresh data sets. Both of these libraries are super useful, but they're also currently super broken. The authors have moved on to other stuff. They did a fantastic job building these, but both of the libraries are currently not maintained. And when dependencies and integrations evolve around a project like this, functionality starts to get lost. So that's where I come in. My focus on this project is going to be modernizing the library's build systems. But to do that, I first need to fix the CI/CD. CI/CD is just, or continuous integration, continuous distribution, is just a shorthand way of saying that when changes are made to the code, then the changes will be integrated in a way that ensures nothing is broken and then distributed. And this screenshot is from my first look at the CI for Wasserstein. Not so great. It is doing better now, but definitely not great. After I've got everything functional, I'll be able to replace the current build system with a modern, more robust build system called Sicat Build Core, which, as I understand it, is actually designed by one of the other mentors and one of my mentors, Dr. Henry Schreiner. And what that is going to do is it will make future updates and further modernization a lot easier. The current build system is extraordinarily delicate, so the robust nature of Sicat Build Core will help immensely. I got started on this project in early May, so I have had some time to run into some interesting bugs. When we package these libraries for distribution, we build for each operating system individually. Oh, well, let me go back. But on that, on the screenshot, it shows, so we build for Linux, too far, and one for Mac and one for Windows. Mac has been a bit of a problem child of this project. But one of the most, I'll get to that in a second, one of the most unsettling bugs that I ran across was from Windows, surprisingly. It worked to start, everything was fine, and then it broke overnight. Nothing would build. This is something that happened downstream. I'm discovering that a lot of packaging is, as Matthew phrased it, a game of whack-a-mole. So it broke. We patched it by just referencing an earlier version of Windows, and then whatever happened to fix it got done. It started working again, so we reversed that patch. I mentioned Mac OS has been difficult. The latest distribution of Mac is, as I understand it, a compatibility nightmare and requires special attention and consideration. Mac also uses a different C compiler than any other operating system called Apple C-Lang. I'm not really sure how to pronounce that. But that was discovering that was a learning experience. And then the final bug that I'm still kind of struggling with right now is figuring out, I believe it's a module. If I'm not using that word correctly, I apologize. But it's called OpenMP, and it is not something that is installed on Mac operating systems. It's a really great tool. It allows code like the Wasserstein library to take advantage of a more efficient way of computing using parallel computing. This breaks tasks into threads, which can be ran independently and simultaneously rather than going like straight down a line of one thing and then the next thing. If you're installing this on a local machine, that's not too hard, but if you want it installed in a distribution-friendly way, that's a little bit difficult. And distribution is the ultimate goal of this project. This, when it loads, is a very broad strokes depiction of my plan for the project. Excuse me. And as I mentioned, the final goal here is distribution. So Wasserstein and energy flow are extraordinarily useful tools, but they aren't helping anyone, or at least certainly not many people, if they aren't accessible to the average physicist. So my plan to get these libraries ready for general distribution started with doing some research and teaching myself what packaging is and what distribution looks like. Then I evaluated both of these libraries to see how I could apply what I learned and identify potential problems. Right now, I am in the stage where I go through and actually solve the problems. And this is probably going to be the longest part of this project. I'm learning a lot. Next, I'm going to take all of the notes with all of the things that I've learned and all of the changes that I've made and compile it into something that will be turned into formal documentation that focuses on what changes were made and why they were made. And finally, we will get to that distribution stage and release Python wheels and I believe distribution packages for other, or for the Wasserstein library, a C++ package for that. And that is me. Thank you all so very much.
Thank you, Jordan. Do you have any questions? Any questions for Jordan?
I have a question.
Sure, go ahead.
You said that you had a problem with integrating OpenMP.
Yes.
But can't you just statically compile it into the binary, or do you want to distribute it through source code also? Like, what was the problem? I don't really understand.
The primary problem is that OpenMP is really easy to install on, specifically on Mac, because in Windows builds and Linux distributions and Windows distributions, it's already available. But for Mac distributions, it just doesn't come with that operating system, so it has to be installed separately. The normal way of doing this is by using Homebrew, but as I understand it, Homebrew, whenever you install a package with Homebrew, Homebrew specifies a lot about the environment that it builds whatever you're installing in. So if you then put that into a package and distribute it, there's a higher chance for things breaking. It's not as stable. And I wish that I knew more about the nuance there, but I hope that answered your question.
Yeah, thank you.
Okay.
All right. Any other questions for Jordan? Thank you, Jordan. Up next is Volodymyr. You want to share your screen?
Hello. Yes.
Yep.
1 second, please.
Sure.
Can you see it?
Yep. Yes.
Perfect. Hello, everyone. And today I'm going to tell you about my summer project, Modernizing Unified, Resubmission and Assignment of Workflows. I'm very grateful to my mentors, Luca Levezza and Muhammad Hassan Ahmed. They're helping me very much. Today's showcase, table of context. In the beginning, I want to give you a little context about the P&R team and what is unified. P&R stands for production and reprocessing. They are responsible for managing data processing workflows, ensuring jobs run smoothly, monitoring performance, troubleshooting issues, and optimizing resource usage across the grid. Unified is the system which operates the workflows. Currently, there are two versions of Unified, the old one and the new one. Unified had became really deprecated, and a year ago, P&R developers started to modernize the code base. As far as I know, last summer fellows were also involved. P&R developers want to finish the migration process from one repository to another by the end of this summer, and I'm responsible for adoption of the adaptation of the old resubmission tool to the new unified. I will talk more about this tool during the next slide. Workflow. To better understand my role in modernizing Unified, it's important to know what a workflow is in the context of Unified. CMS detectors collect tremendous amounts of data within each collision experiment. Workflow is a chain of data reprocessing. Each stage is called a task, and within each stage, data is processed and only important data is extracted. Errors may occur, and usually problem could be resolved by changing the parameters. P&R developers made a tool called AutoACDC. It resubmits tasks with certain parameters. Currently, a user must manually input parameters for resubmission, but automation is a key aspect of my project. First, we will collect statistics on the parameters that are usually successful for specific error codes. Based on this data, we will develop tool that can automate resubmissions with minimal human intervention. This tool will implement smart decision-making process to select the best resubmission parameters, significantly increasing the success rate of resubmitted tasks. The goal is to reduce the manual effort required by the P&R team, allowing them to focus on more critical tasks. During the development process, I'm going to get practical skills in modern development practices like CI/CD, Docker virtualization, unit tests, and more. Thank you for your attention. Feel free to ask questions if you have.
Thank you. Any questions for Volodymyr?
I'm sorry, I have a really stupid question. What's your presentation template?
Was my presentation updated?
Template.
The template. What template did you use?
I have used a template from a PowerPoint, but I guess it's not a default one. It's from a public workshop, I guess.
Okay, thank you.
Any other questions? All right, thank you.
Thanks.
Okay, up next is Khan.
Hi everyone, my name is Khan. I'm a senior here at the University of Colorado. And for the summer project fellowship, I'm going to be working on improving the analysis grant challenge by implementing a new machine learning workflow specifically to the graph neural network. And I have been working with Elliot, Alexandr, and Oleksandr as my mentors, which is something I'm really grateful for. So I just want to firstly give a quick overview about the analysis grant challenge on the HEC. So the HECs, we aim to investigate, develop, and as well as improving the end-to-end analysis workflow. And we are also preparing for the high luminosity LHC, which is going to be coming in 2029. And we expect that we're going to get lots of data after that, as well as the events, the backgrounds, and it also give us more chance to observe the rare decay as well. So as a result, as an HEC, we want to take that into account and try to prepare the pipeline such that it will reflect on the user's needs, such as an interactive interface, the data access, or any other processing as well. Sorry, next slide. And usually we have a lot of different analysis going on, but the one that we have been focusing on is a TT bar analysis, specifically to the semi-electronic TT bar production. So if you take a look at the pictures on the top left, we could see that from the TT bar production, we have a top and an anti-top part. And for the top part, it's going to be the leptonic side. And the final product of that one is going to be quark jet, lepton, and neutrino. And for the hydraulic side, on the bottom of the diagram, we're going to have two W jets. And another one is going to be quark jets as well. So before we could really get any physics inside all of it, the main problem with this analysis is that we have to correctly classify all this jet, because the detector got lots of jets coming out of it, but we don't really know. We can't say for sure which jet is coming from which parent. So there are different ways of doing it. The most basic one is to use the algorithm combinations, and this one is a non-machine learning method. So what it does is that we use AK combinations to create a tri-jet system, which is including 3 jets. And by going through different permutations of those jets, we can find the highest PT candidates. And once we find the highest PT candidate, we can use that tri-jet system to calculate the mass, to calculate the reconstructed top mass. And if that's pretty close to the top quark mass, do we know it's likely that that specific tri-jet system is going to be, 2 of them is going to be W jet, and 1 of them is going to be quark jet, which is on the bottom of the diagram that you could see. And another way of doing it is to use the simple machine learning, which is the boosted decision tree. And what it does is that we're trying to label those jets beforehand, rather than just create a tri-jet system and then calculate the PT value. So in the machine learning of the BDT, we're gonna have all the permutations of each event. So let's say if we have 4 jets in the event, we're gonna have 12 permutations, because we have 2 indistinguishable W jets, one B top jet from the hydraulic side and another B top jet from the leptonic side. And after we have all the permutations of the jets across all the events, we're also gonna have features of the machine learning. And in this case, the one that we have been implemented before, we're using 20 features, and that include the PTs of the jet, some other VTAC value, the quark gluon discrimination part, the combined mass, the combined PT, or the delta R value between all those jets. And yep, let's go to the next slide. Another way of doing it that I've been trying to do in this summer is to implement another more complex machine learning, which is a graph neural network. It's actually pretty similar to the BDT, but it has a slightly different about the way that you're setting up the data as well as the way you're processing it. So in this one, we're trying to represent the TT bar production as a graph. We're gonna have a node and as well as an edge features. In this case, we can imagine that every jet in the TT bar production could be implemented as a node of the graph, and the node features is gonna be PT of the jet, the eta values of the jet, the phi value, or the mass value. And for the edge, it's gonna be the connection between the jets in the same event, because we have tons of events, and each event is gonna have its own jet. So technically, the edge feature is gonna say that these 4 jets or 5 jets is gonna be connected together only on the same event, but not across the event. And we can also try to implement the edge features, such as the delta R value between jets, or the combined PT or the combined mass between jets. And after that, what it does, it do something like a massive passing, which is the way that they learn how the jets interact with each other. And by doing that, we can learn how to classify jets more efficiently. So at the end, what we're gonna get is that we're trying to classify each jet into 4 labels. The first label is gonna be the B top from the leptonic side. The second label is gonna be B top from the hadronic side. The third label is gonna be the W jet, and the fourth label could be other jets. That is not our intrastate jet. So as you can on the bottom left of the slide, you can see that there's some architectures of JNN, because technically there are tons of variations about how you could build the graph neural network, and it depends on the task of the problem. And in this case, by implementing it to the physics problem, I feel that's what I'm trying to do it, such that it can reflect with the TT bar production we're interested in. And on the right side of the slide, you could see the graph that compare the reconstructed top mass between 2 methods. The first one, the orange line is going to be using AK outward as a trijet system to reconstruct top mass, and the green line is going to be, the blue line is going to be the truth table, and the green line is going to be the result that we got from the BDT. So you could see that there's a significant improvement moving from the trijet system and using the machine learning BDT. And unfortunately, I don't have any results from the GNN yet, because it's still something I'm implementing on it. But hopefully we're gonna get the same pretty similar performance, and potentially the improvement from the BDT model as well. So the objectives of this event is that firstly, I'm gonna try to implement the GNN technique into the pipeline that we already have, and I'm also gonna try to explore more about more complex GNN architecture as well. For example, we could use a self-attention, or incorporating the edge feature into the GNN itself, such that we can reflect the physics phenomena of a TT bar production. The reasons that we want to use graph neural network over the BT is that in the futures, we can expecting that with a lot of data coming in 20 from the high luminosity HLC, we might need more robust and refined models such that we can do the analysis sufficiency. For example, we can try to separate the signal from the breakout more sufficiency beside using the BDT model. And I also want to mention some of the library that I have been using for building the GNN. So we have a scikit-learn, which is a simple Python library that we use for building the matrix and the model. We also have XGBoost, which is the first machine learning implementation that we used, and that's technically going to build the model for the prediction as well as the optimization. We also have DAOs that help with the scalabilities of the machine learning. We also have NVIDIA Triton, which is like a inference infrastructures, and it helps a lot with like speeding up almost like every computation. And PyTorch is the mainly framework that I use to build a GNN rather than like a TensorFlow. And that's everything. Thank you.
Thank you, Khan. Any questions for Khan? And I just want to say I'm envious of your background there, Khan. So looks like a nice setting.
So. It's a really nice day here in Colorado. So I like
it appears to be. So
yeah.
All right. Up next is Viktoriia. Viktoriia, you want to go ahead and share your screen?
Okay, hi, my name is Viktoriia. I'm from Kyiv Polytechnic Institute. My mentors are Alexandr Karatelli and Marco Andorne. And today I'd like to present the project Embedded Software Application for a RISC-V based system on chip, SoC for Large Hadron Collider for LHCb Velo for Velo detector. From the microelectronics section at CERN. So, we specialize in designing integrated circuits that are crucial for high-energy physics HEP experiments. Most of our designs are highly specialized application-specific integrated circuits, ISICs. Illustrated by the extension in the CMS Complex-Magnum solenoid detector at the Large Hadron Collider. In the image on the right, you can see an example of ISIC that have been designed by the team and how those chips are installed in the CMS detector. One of the 4 experimental on the Large Hadron Collider at CERN. Also, as the complexity and scale of ISIC design continue to grow, we are moving towards abstract design methodologies that enhance modularity and programmability. Our current focus is on integrated system on chip techniques to efficiently consolidate multiple functions onto a single chip while enabling programmability on detector IC. So we are currently developing a platform aimed at automating the generation of SoC hardware descriptions and software stacks. As a part of this effort to explain programmability options of the specified platform, it's necessary to develop a technological concept of high-level C++ coding can be used for such interactions, as well as development of codes for simulating and testing the generated SoC hardware. It's supposed to develop a conceptual prototype for integration of firmware applications written in high-level C++ with a simulated microcontroller based on RISC-V architecture. This will help identify problems at the design stage and ultimately make improvements. Furthermore, it's crucial to understand the software and effectively use the libraries provided for future application development. And now I'd like to walk through our project's key stages. Firstly, begin with understanding how to execute C++ software on the simulated hardware of custom RISC-V processors. This enables the design of a comprehensive framework for software interoperability across various project abstractions. The next milestone involves creating an application prototype to showcase specific functionalities, also setting the stage for evaluation and refinement. The next step is to develop and to test multiple C++ routines adapted for peripherals, testing and system-on-chip functionality, validation on the simulated hardware environment. In fact, it's supposed to implement a specialized C++ application for the SOC, serving as a prototype readout ASIC for a Large Hadron Collider, Velo detector. So these efforts collectively demonstrate our dedication to innovation and practical application within the realm of embedded systems. Thanks for your attention.
Thank you, Viktoriia. Any questions for Viktoriia? All right, thanks again. Next up is
Mykhailo or Michael.
Mykhailo. Oh, Michael. Sorry, I was afraid I was going to butcher
not
it.
a problem. I should have written it in more English-friendly way.
I wasn't sure, so but
Yeah.
go ahead and share your screen.
Yeah. One moment. So my project is my name is Mykhailo Varvarin. I am a second-year master's student at Kyiv Academic University, Ukraine. I study applied physics. My project is extending the Alpaka performance portability library for the with CUDA Cooperative Groups for the CMS pixel reconstruction. And my mentors are Yizi Vyskochil and Volodymyr Bezguba. So what is Alpaka library? It is a header only C++ 17 library for accelerator development. It aims to provide performance portability across accelerators through abstraction of the underlying levels of parallelism. So it supports various accelerators. It's both the GPU accelerators, so NVIDIA CUDA, AMD HEP, and Intel SYCL, and CPU accelerators, so that's OpenMP, STD threads, part of C++ standards library, and Intel TBB API. And its largest features is that you can recompile your code from using one accelerator to using another with just changing a few lines. A typical kernel in Alpaka looks something like this. You don't have to look that much into it, but it's basically a kernel that is executed on each and every thread of your program, and this one adds two vectors and stores it into a third vector. Looks like modern C++. CUDA Cooperative Groups, which I will be implementing in Alpaka, are a new abstraction level that allow for better synchronization between threads. Traditionally, CUDA had only synchronization within one block. So on NVIDIA GPUs, when you run something with CUDA, you have a single thread. Threads are grouped into blocks, which they aren't directly mapped into hardware streaming multiprocessors, but similar to them, each block can only run on a single SM, but that theoretically can be more than one block per SM, depending on your kernel. And then you have multiple blocks within a large grid spanning across the whole GPU. Traditionally, CUDA had only block level synchronization, so you could only synchronize up to 1024 threads. That's the maximum number of threads in one block. That's a problem. For example, if you have some kind of algorithm that has multiple steps, that it's iterative, and each iteration is dependent not only on the result of previous iteration on this thread, but on also on the other threads in the grid. But the only way to do it was either to just skip some synchronization steps and synchronize only within one block, but it's not the whole grid, or you could launch a kernel within a new kernel within a different kernel that's called dynamic parallelism, but it has a really large overhead because you need to load a new kernel that invalidates all the cache, and so overhead can be quite large. Cooperative groups add support for multiple new levels of synchronization, both on the sub-block level, so you can synchronize basically any power of two number of threads less than 1024, and you can synchronize the whole grid. Synchronizing on sub-block level doesn't necessarily bring a lot of performance, but with some clever optimizations, you can win some performance with it if you only need to synchronize a few threads at a time. But the whole grid synchronization is quite a game changer because it allows you to not use dynamic parallelism, so no cache invalidation, and potentially much better performance. So my task within for this project will be to add support for CUDA Cooperative Groups in Alpaka, so you can launch a CUDA kernel that supports them within Alpaka, and you can use their features. First and foremost, grid synchronization. For the other features, we will determine it later whether they are needed in Alpaka or something else should be a priority. After this, after I will, if there will be time, I will add support for this grid synchronization in the CMS PataTrack application. It's a pixel tracking application for the CMS accelerator in which is a part of Large Hadron Collider, which already uses Alpaka. Also, if there will be time, I might potentially explore adding cooperative groups emulation for the CPU accelerators, because Alpaka aims to provide an ability to run a single kernel on all of its accelerators. So there will needs to be some kind of support added for the CPU accelerators. Thank you for your attention.
Thank you. Any questions? Okay, thanks again. Next up is Alexander.
Yeah, I'm here. Just a sec.
Sure.
So. Hi. So yeah. I'm really glad to present my project. My introduction talk. So today I'm going to talk about quite long name of my projects: advanced ML techniques and dual-readout systems for Electroweak jet identification and particle flow enhancement for future collider detectors. I'm a student from the University of Manchester. I'm an undergraduate student, and I'm grateful for my mentor, Christopher Tully. So first of all, I'm going to talk not only what I'm working on, but also in what part of the detector I'm actually curious about. And I'm basically curious about dual-readout systems. That's systems that are in calorimetry, that systems that addresses the challenges of the challenge of measuring simultaneously two signals, Cherenkov signal and scintillation signals, when photons go through the medium. Basically, it's vital for construction as it provides us with accuracy, and not also with accuracy, but also with possibly to differentiate the hadronic part and electromagnetic part of the shower. And therefore, going into deep, we start talking about photon pointing mechanism. That's techniques that is uses to determine the direction of the photon from which it's originated. It's vital for construction, and not also for construction, but also for defining the characteristics of the photon, and to define the centroids or central of gravity of the shower. We are considering two parts of the dual-readout system. Basically, two parts of the depth, so the front depth, the front part and the rear part, where the position of the energy of the photons is going, and determine the centroids. We can, so as I said, basically reconstruct the direction of the photon. And first goal is Monte Carlo and data simulation. So basically, I'm going to use quite sophisticated methods. So that's most Monte Carlo, and also I need some environment, and I will going to use a quite popular environment for that. That's Jean 4. Which is quite popular in particle physics due to the quite broadly framework for construction of the events and propagation of particles through the medium of the detector. And basically, it's I need that to not only to reconstruct, but also to simulate data for and create the training data set for my future ML model, machine learning model. So yeah. So starting talking about the machine learning in photon pointing, I'm going to basically use quite popular toolkits such as TensorFlow and PyTorch with the syntax of C++ and Python. In the variety of neural networks and techniques that can be used, basically I'm considering right now the CNN or convolutional neural network that's already used in Atlas, for instance, for identification of electrons. And I will try to do it as possibly adaptable for different types of data. But main goal is not only to train my data for defining the sinusoids and to train it to finding the direction of my for reconstruction of the photons, but also for determining the thickness of the front of the front depth of the calorimeter for the deposition of the energy of the photon. And it will take, so it will be more on the week 3-4, so quite soon. For now, I'm basically familiarize myself with Monte Carlo techniques and also already working on the installing of the software for based on also on Jant for simulation. So yeah, and that's my references. Thanks a lot.
All right, thank you. Any questions? Okay, that's our final talk for today. Thank you to all the fellows for your talks. Thanks to all the mentors and everybody else that showed up for the talks today. We'll have another set upcoming next week. So thanks, everybody.
Thanks a lot.
Everyone. Nicely done.
Thank you.
Bye.
Thanks, everyone.
Thanks.